Hello friends, welcome to my channel Code Destination. So as we are continuing this challenge one code one day, and we are taking the topic binary search algorithm. So we already discussed I think three variant of binary search in previous days. So today topic we are choosing is the 2D array. Basically we will take the question on like 2D array, how we can apply the binary search on the 2D array. So this is the last question of binary search of the binary search algorithm series. So today we are considering this question 240 question number name search 2D matrix. So basically we have given this matrix which is basically sorted in the row wise and column wise manner, because we can see for the first row is sorted from left to right and the first column is sorted from top to down. So basically this array is sorted. If you take any element like any row, so that row is sorted from left to right, and if you consider any column, so that column is sorted in ascending order from top to down. So basically we have given this array, this matrix, basically 2D array, and target we have to find, like we have to return whether the target is present or available in this matrix or not. If it is available, then we have to return true, otherwise false. So explanation is very simple. So maybe we can discuss how we can approach that problem, like as like we approach in the 1D array. So I already draw the diagram for explanation. So here we can see first like we will connect the 1D approach to in the 2D approach basically. So first we will think how we apply binary search in the 1D approach, then we will try to connect the same intuition, like almost same intuition on the 2D like array, basically how we can think that approach. So basically in the 1D array, what we generally did, we just define the boundary, like because we know it is 1D, so just it is one dimensional. So just I took the boundary element like this zeroth element, the last element, like here. Like it is a normal binary search. What we did, I just explained why we did. So we just take the boundary from ith and jth, and we generally found the middle point, because in the 1D direction like 1D array, basically we prefer to find the middle only, because after finding the middle we generally compare this middle with the target. Like suppose in this case the target is 9, so we compare this middle element 6 with 9, and after the comparison we decide which half we can like ignore. Either this half we can ignore or this half we can ignore, and once we ignore that half we can move our like search search range in the next half. So this is the approach basically we discuss. So I will just connect that approach, the 2D array, how we can think. So first of all we define the range using I and jth value, but in 2D array, like we know it is containing row and column. So basically, and for like defining boundary we have four options, like this is the first, this is the second, and this is the third, and this is the fourth. So we have option in this case for defining the like boundary. Like in the first 1D array we define generally boundary like I and jth, but in this case from where we can start, we have to think. So suppose I take I and j here, I here and j here. If I think like that, then whether it will be good or not we can decide. Suppose I take this I here and this j here. So like why I choose I and j here, in the 1D array case, because like we can see, like if you choose I on the 0 index, so after that all the element is increasing, and if I choose the jth element at the last, so that before that all the element is decreasing. So this is the property it is following in the 1D array. So we will choose the same boundary which is following this type of property. So we can think, if I choose this ith element, so like in this case in this direction it is increasing, and in this direction also it is increasing. So it is sure that this is not a good like boundary for the ith, because for both direction it is increasing. Okay, and we have to think this in a 2D manner, because in the 1D manner we are just one direction, so we just think whether it is increasing or not. But in this case we have to think both rows and column. So in this case we can see like it is increasing like from left to right, and from top to down also it is increasing. and from jth index, like we can see, it is decreasing in this direction, and it is also decreasing in this direction. So basically, in the 1D array, we just define this m, and with the m we can say that we can ignore some of the part. But in this case, suppose I choose this boundary, so can I ignore any part? Suppose in this case my target is 6, and I choose to start this from here. Like there are 4 possibility, but suppose I choose from here to start our searching. So like we generally compare this one element with the 6. So I saw this one is less than 6, but with that result we can't be sure that whether we have to move that side or we have to move that side, because there are two possibility: either we can move in the row direction or in the column direction. But with this conclusion, like if I compare the 1 with the 6, like 1 is less than 6, so we can't sure that we have to move in the row direction or the column direction, because both directions are increasing. So we are not sure. So definitely it is not a good point to start. So the second point is this one. Suppose I choose this 10. Okay, so this 10 I just compare, like we can see in that in the direction it is increasing, but in this direction it is decreasing. So basically it is following that type of property in the, like we follow in the 1D array, like from I to like left to right it is increasing, and right to left it is decreasing. So in the one direction it is increasing in this case, and in the one direction it is decreasing. That is just intuition, but we can think logically as well. Like if you compare this 10 with a 6, then what is the result? This 10 is greater than 6. Okay, and we know if this 10 is greater than 6 and all the it is increasing this direction, so all the element like 13, 14 and 17 is definitely greater than 6. So we have only one option: we can just go like bottom to top. So in this case, like we are just ignoring one whole row in that case, correct? So in this case, like we can ignore one row. So it means it is a good point to start from here, because in like in 1D array generally we just ignore half part, but in the 2D array either we can ignore whole row or whole column. So in which case like in all the cases in which we can ignore either row or column, that is a good place to start. So this is the first place from where we can start. So what is the second place? Maybe you can think, like suppose I start from my I pointer is here and j pointer is here. I am starting from this boundary. Okay, so we can see like in this point, in from right to left it is decreasing, and from bottom to top it is also decreasing. So basically, suppose I choose this 17 and I will compare this 17 with 6. So 17 is greater than 6, it means we have to choose the less value. But in the both cases we are choosing the, like we are decreasing, so we can't say that whether we have to move top or whether we have to move left side. So from this index we are not sure, so that is also not good index to start. Suppose I choose this I as jn here. So suppose I choose this element, and we can see from right to left it is decreasing. Okay, it is decreasing, and from top to bottom it is increasing. So it is also a good point, because for both direction it is one direction it is decreasing, and for one direction it is increasing. Like in the 1D array, for one direction it is increasing, and for one direction it is decreasing. So whether this behavior have, that index is good. But we can also think logically, like this 11 element is greater than 6. So we are sure that all the column, like basically all this column is greater than 6, because it is increasing from top to bottom. So just we can ignore this whole column in that case, and we can just move and the left side. So like if you are choosing this index, so we are like after comparison we are sure that we can ignore whole row. But if we are choosing this index, like this corner, like this boundary, then we are sure that we after comparison we can sure that we can ignore all the column. So basically there are two correct point to start boundary. Like first is this one: either we can start from this index, or we can start from this index. So that two index is good, because this is following the property which follow in the 1D array. Like in 1D array when we define the boundary with I jth, So we can see some observation, like from left to right it is increasing, and from right to left it is decreasing. So this property should be followed when we choose any boundary case in this 2D array. So same approach we will find, and we will approach like how we can solve that. So some observation I can show you here, like when suppose in this case that two cases we can choose. So like in my solution, maybe I am choosing this one, this second case. I start from here. So what we will do generally, like we will just take this element. Okay, we will compare with target. Suppose in my case the target is this one, this 6 is my target which we have to get. So I just compare this 11 with 6. So 11 is greater than 6, so I just ignore all this column. I just move my j from here. So next I will search this element. Again I will search, like compare this 7 with 6. So 7 is greater than 6, it means all the column again I will ignore. So I will just go left side. So I will just decrease my jth value. So I will start from here. Again I will compare this 4 with 6. So in this case 4 is lesser than 6. So it is sure that all the element before that is less, because in that case like it is decreasing. So all the column, like here all the thing is decreasing here. So basically all the column, in this case this one only remaining. So I will just ignore that, and I will move my ith pointer in the next element. So I will just start from here. So I will again compare this 5 with 6. So 5 is less than. Again I will ignore all the like column value just before that, and I will just move my row value. So once I reach, I will just return that. So same approach I will follow, and in the code, maybe once I write the code, then you can connect with logic. Okay, so what we did, I just defined my boundary with I. So my I is suppose row defining from 0, and j is my matrix, the column. Okay, so I just define my like a starting point, basically boundary. So I choose this boundary. In this case, like we have two options, this one or this one, but we are choosing this one in my case. Okay, and yeah, what is the condition to stop the like with this check, like I, because generally we are just comparing and we are moving the j and I. So we are starting here. So my like j value is showing the column value and I value is showing the row value. So j will move from left to right. It means still it will run till it will not go the out of the boundary. It means till it is greater than or equal to 0. And I is moving from top to down. It means it will be moved till it is less than or equal to the column size. Okay, so I will define that boundary in while loop, like we'll did in the binary search with 1D array. So my I will greater than or equal to 0. No, sorry, j, because j is dependent in the column, and I is less than or equal to okay, matrix dot length, it is a row value -1. So because it is 0 bits indexing, so this is my boundary case. So I will find my element here. So I will find my element, suppose ith and jth element. Okay, so what is the case if my element is equal to target? So in that case I found, so I will directly return true here. And if my element is greater than target, so in that case what we can ignore, basically my element is greater than target. So if 11 is here, 11 is greater than target, like greater than 6 in this case, so basically all the column I can ignore. So basically I will move my j pointer, because which is representing the column j minus minus. And if the opposite case, it means if my element is less than, so I will just move my I pointer plus plus. So in this way I can move my both the pointers, and once it is reached at that element which is equal to target, that case it will return the true. And at the last, if I didn't got the element, I will return the false here. So I think that's it. It is very simple. Let me run it. Yeah, so both the test case passes. Let me submit it again. Yeah, it accepted. It's taking 5 milliseconds and beats 99.90 users of Java. So you can connect this code with the logic, like as I discussed already. Like from first we can think from where we can start. Like I can just write here. First we decide our boundary I and j value, and ij value how we can decide. Like I compare with this 1D array. If I define ij, so like for one direction it is increasing and one direction it is decreasing. So on this behalf we can decide, like for one direction it is increasing and for one direction it is decreasing. So this is both like two basically boundary, like 0, and if my suppose row, this is the row size and into m like matrix. So this will either it can start 0th row and m minus 1th column. This is first case, or it is n minus 1th row or 0 column. So in both case we can start both boundary, which is feasible, which is following this property. And the second case, we are just in the first 1D array we find the middle pointer, and with by comparing the middle element we can ignore the either one half or this half or this half. But in this case this is 2D array, so we can ignore one row or one column. So basically we can compare this itself, this element like this 11 with the target, and we can by comparison we can show that if it is getter, then it means it is ascending order sorted, so all the element will be getter. So we can, one case we can ignore either like whole row or whole column. So we will think either ignore whole row or whole column. So this two case we can think only, and we can apply the algorithm directly here. So I hope you understood the intuition and how we solve that question. So if I'm talking about the time complexity, so we can see here like this loop is moving from j like greater than 0 and I less than matrix minus 1. So in the worst case I can think, if you visualize this matrix, like we start from here, and suppose in the worst case we can think like this is our matrix, suppose. Okay, and suppose I start here and my target is, suppose in the worst case it is here. Okay, so this is the worst case when we will run our like search algorithm, like it will take like more time. So what we are generally doing, like for one comparison we are just ignoring whole row or whole column. So basically either we are moving this direction here to here, okay, in the worst case, or we are moving this here to here. So in both cases it is just comparing, like checking total how many operation we are, it is taking m in m plus n, because in every check we are just ignoring whole column. Suppose in this case we are ignoring this column, again we check and we ignore whole column, then again we check, then again we ignore this whole row, then we are basically first we was moving this direction, then we generally we shift in this direction. So in the worst case either we can start from this corner to move whole like column, or we can start from here and whole row. So basically in worst case we are taking this m plus n operation. So this is m plus n if where m is row and n is column, basically for the matrix, and the time complexity will be um, big O of m plus n, where the m and n is the row and column. And if I'm talking about space complexity, so there are no extra space we are using, so it is a constant space operation. So it is a big O of m plus n and big O of one space complexity solution. So I hope you understood the intuition and how we build the logic, which by comparing the 1D array logic, and how we implement in the code. So if you like my video, please like on the YouTube and share it, and also subscribe for future videos. Thank you.